Welcome to Maths with EJD. We're still talking about non-linear programming. Non-linear programming. And we have considered different methods for solving this, like the penalty method. We have the barrier method. Then we have the Karush-Kontoka conditions, which generalizes the Lagrange multiplier that we learned about under constrained optimization methods. And now we are talking about evolutionary algorithms. Evolutionary algorithms. So, um, since we have already dealt with penalty method, we've dealt with barrier method, we've dealt with KKT conditions, we are going for evolutionary algorithms now. And these evolutionary algorithms, uh, they actually, we're going to consider five of them in all. So, but okay, let's go for that for evolutionary algorithms. So, that is the next thing. So, in the next 5 videos or so, we'll be talking about evolutionary algorithms for non-linear programming, like that. Okay, so let's move to that now. Evolutionary algorithms. So I'll just give some key facts about evolutionary algorithms. Evolutionary algorithms, we can call them EAs, right? Are a class of optimization techniques inspired. So they are inspired by the biological idea of natural selection, inspired by natural selection. That's why it is evolutionary, by the natural, by inspired by natural selection, and it's well suited for solving nonlinear programming problems with complex, non-convex, and high dimensional high dimensional search spaces. Okay, so they operate they operate through iterative improvement, through iterative improvement using mechanisms such as selection, mutation, crossover. Now, we've seen this before under one of the previous videos, but not for nonlinear programming. Mutation, crossover, and reproduction. Okay. Now, what are the key variants of this? Key variants of evolutionary algorithm include, in fact, in this video, I'll list the ones we're going to consider in this playlist. First of all, we're talking about, just like you've seen, this one is about simulated annealing. Simulated annealing. There's also one called evolutionary strategies, which I'm not going to be talking about here. After simulated annealing, we're going for taboo search. Then after taboo search, we'll be going for um after taboo search, we'll be going for genetic algorithm, I believe. Genetic algorithm. Then after genetic algorithm, we'll talk about um after genetic algorithm, we'll be going for particle swarm optimization. Particle swarm optimization. And lastly, we're talking about differential evolution. Differential evolution. Of course, we have evolutionary strategies, which I'm not covering in this playlist. So I'm not boy, you should just know that it's there, right? Of course, simulated annealing, SA, table search, TS, genetic algorithm, GA, particle swarm optimization, PSO, and lastly, differential evolution, DE. And then we go on to talk about other things as that surround this. So each of this method, or I guess I should still, I mean, I just mentioned that each of this method is tailored for different problem structures. Okay. But then, unlike, uh, unlike gradient-based methods, evolutionary algorithms do not require derivative information, derivative information. So it doesn't matter if the problem is not this differentiable or not. Does not require derivative information, making them effective, making them effective for discontinuous, making them effective for discontinuous, multimodal, and constraint problems. And constraint problems. Okay. Um, Now their ability, their ability to maintain a diverse population helps avoid local optima. So that's usually a problem. You can get a local optimum or a local minimum or maximum and get trapped there without being able to get out. So these methods are really good to actually help with that. So the ability to maintain a diverse population helps avoid local optima, making them widely used, widely used in engineering design, engineering design, machine learning, and financial optimization. Okay, so with that said, let's go for the first method we'll be considering here. Okay, we're talking about simulated annealing for non-linear programming. Simulated annealing. Okay, so simulated annealing, SA for short, is a probabilistic probabilistic optimization technique. I mean, we've seen this before under derivative free methods. Talking about optimization techniques, derivative-free methods. I think it was the first or so we saw. Simulated annealing is a probabilistic optimization technique inspired by the annealing process in metallurgy. So it's a concept from cooling in metallurgy, annealing process in metallurgy. Okay. It is particularly, it is particularly, it is particularly useful for solving complex, complex nonlinear programming problems where traditional gradient-based methods. So gradient-based methods are more like the general ones, the very traditional ones that we think about when we think optimization. Traditional gradient-based methods. So where traditional gradient-based methods struggle due to non-convexity. So non-convexity makes it difficult to find an optimum solution. So makes it methods struggle due to non-convexity, discontinuities, because those methods work better for continuous functions, or even struggling due to multiple local optima, which is the issue with non-convex optimization. All right. So with that said, let's talk about the algorithm overview for simulated annealing. Of course, we've seen this before, but here we are considering it for nonlinear programming. And as usual, the first thing is initialization. Initialization. So of course, there's always a starting point. So here you start with an initial solution, X naught, and a high temperature and a high temperature. Since it's about metallurgy, cooling metallurgy, so initial solution X naught and a high temperature T naught. Okay, that's the starting point. And after that, we go for number two, which is the neighbor selection. Like we've seen before, neighbor selection. So as far as neighbor selection goes, you generate a neighboring solution, a neighboring solution called that X prime using a small perturbation. So you can, if your initial solution X is like 2, you can make it 2.1 or 1.9. Just shake it up a bit using a small perturbation. That is the neighbor selection area. And then we go for the next part, which is the evaluation. So you do some evaluation. And at that point, what you're going to do is to compute the objective function values, compute the objective function values, f of x and f of x prime, that perturbed one. And then we go for the next thing, which is 4. You have an acceptance criterion. Acceptance criterion. So how do you know that you have got the solution you want? So you say if if f of x prime is better, you accept it. So accept it. If not, accept it we said it is probabilistic, right? So you accept probabilistically, okay? Using the metropolis criterion. Metropolis criterion. And the metropolis criterion is the probability of acceptance, probability that you accept that which is not better is actually e raised to power f of x minus f of x prime. That's like delta f of x all over the temperature. Okay, so that's like that's the criterion for acceptance. So we have that. And the next thing after this is number 5, and that is termination. Okay. For every, you said it's iterative, right? So once you have a stopping criterion, once that is achieved, there's termination. So what we do here is we stop when temperature T reaches a minimum threshold, when it reaches a minimum threshold, or after a fixed number of iterations. Okay, now let's consider a problem. So this example borders on minimizing a non-linear function. Okay, so consider the non-linear function f of x equals x squared plus 4 sine 5x plus 3 cos 3x, and this happens for x belonging to the closed interval -5 to 5. So to deal with this, then we'll be talking about okay. Okay, let me go for this. Step 1, as usual, step 1 is initialization, just like what we saw now. Initialization. Okay, so here you choose an initial solution. X naught is equal to 3. Then the next thing is we set initial temperature. T naught is equal to 1, and cooling factor alpha equals 0.9. So we need a cooling factor. So the next thing we want to do is to do the iterative search. Step 2, here we have the iterative search. So at each iteration, first we generate a neighbor, and the neighbor is something like x prime equals x plus a random perturbation, and that perturbation can be something like a Gaussian noise. Okay, so we have that random perturbation. So after this now, we can have okay, let me just go on with this. So generate a neighbor. After generating a neighbor, you compute function values f of x. And now I'm just writing this out because I'm going to use Python to do this. because we've done a bit of this before. So compute function values f of x and f of x prime. Okay. Then the next thing we want to do is accept accept x prime if it improves f of x. Otherwise, accept it probabilistically. And finally, we reduce. So reduce t as t equals alpha t, meaning that maybe tn plus 1 is equal to alpha tn, if you like. So so it means that the temperature will be reduced by the factor 0.9. So it's since we started with 1, so the next temperature would likely would be 0.9 for sure. So with that done, then the next thing we want to look at is the convergence. That's step 3. So for step 3, our focus would be on convergence. Of course, at that point, we'll be talking about stopping criterion and things like that. So step 3 is convergence. Convergence. So after running for sufficient iterations, simulated annealing converges to an optimal or near optimal solution. Optimal or near optimal solution. Okay. I mean, with this now, let's see what the Python code is saying in this situation. Simulated annealing. Okay, so this is it here. 82 lines. Of course, it could be better if we try to optimize the code. So the function we are dealing with is in line 6, x squared plus 4 sine 5x, then so 4 sine 5x. Okay, I think mm, there's an omission somewhere. I guess I need to. So 4 sine 5x exponent 0.2x squared. I think this question looks a bit different. Um, okay, I guess let me just conform it with this. So x squared plus 4 sine 5x. I think we don't have this part. We do not have this part. And then we have 3 cos 3x, and we do not have the other part also. So yeah, that's the function we have. And then you have all the other for simulated and number of iterations, which we can vary temperature. In fact, the temperature here, the other side, we said the temperature should start from 1, and then the alpha initial is 0.9. Okay. Alpha final is still that's 0.9, right? So maybe we can stop this one at 0.99, right? Stagnation limits is 100. So, I mean, you can study this code later. You can find it on Facebook, copy it out and run it. So you see the limits between -5 and 5. So I just run this and see what that gives us. Okay. So you can see how that goes. Now you see, those those stars you see in red now. Those stars are actually possible solutions, right? Because they are minimum points. But the trouble is that if you are using a method that is not good enough, this one here can be given as the minimum point, and this one can also be given as the minimum point. Though this minimum point is lower than this minimum point, but then you see the global minimum is this cross, and that's the global best solution, and that is what simulated. That's why these kind of methods are about. So you don't get stuck in any minimal point because you are there to search for all the possibilities. So at the end of the day, you discover that the value of x is 0.9499, and f of x evaluates to -5.9680. All right. So that's what the global solution is. So those red ones are possible solutions, but they are not the global. They are minimum point, but they are not the global minimum or the global minima, if I may say. So for the final result, we have -5.9680 for the function f of x. and X itself is 0.9496. That is where it gets to a global minimum. And that happens in 5 runs. So you see the first one, you have minus 2.8412, which corresponds to 2.2198. And then it goes all the way down to where we finally get the optimum, the global best solution, which we can now accept. So with this now we can go back. So you try to take time study this code. You can find it on Facebook, but not on YouTube because of the some special characters here that YouTube descriptions do not accept. All right. So let's go back to where we're coming from. Um, so from the Python code now, so solution from the Python code. So you see that X star, if you like, is equal to 0.9496. That is like the global. Okay, well, the collection of the two is what we can call our global minimum, right? And then you have f of X star, which is equal to minus 5.9680. So this actually would be our global minimum, if you like, optimum global minimum. So with that taken care of, we can also try to see some kind of summary of this whole thing. So let's look at some key advantages and applications of the simulated annealing method. So key advantages and applications. So the first thing is that it handles non-differentiable, discontinuous, non-differentiable, discontinuous, and multimodal functions. So you can see that function is multimodal because there are many minimum points, but there's only one global minimum point, right? That is the minimum of minima, so to speak. Then actually avoids local optima. So you can see that those optimum points that are higher than the global one, they were reached at some point, but the search does not get trapped in those places because they are not the ultimate minima. So avoids local optima, local optima by probabilistically accepting worse solutions. So it accepts a solution that is not good enough with a measure of probability, not with full assurance, you know, and then it keeps moving. So it is used in engineering. It is used in engineering design, just like we said before. It is used in machine learning. Okay. It is also used in, oh, okay, machine learning hyperparameter tuning, right? It's used in machine learning hyperparameter tuning and financial optimization, like we said before, financial optimization. Okay. So this approach provides a robust optimization framework for solving complex nonlinear programming problems where traditional methods may fail. Now, can we talk about some practice question? So we go for practice. So some I'm going to just say it, and some I'm going to write. Maybe I write only one. So the first question is, what is the primary motivation behind using simulated annealing for optimization problems, especially in nonlinear programming? Two, in the simulated annealing algorithm, why is it necessary to accept a worst solution with a certain probability? Three, what happens if the temperature in simulated annealing decreases too quickly? What impact might this have on finding the global optimum? Okay. So let me just drop this one question and then that'll be all for now. Okay. So consider consider the objective function f of x equals x cubed minus 5x plus 2. Okay. And the search space, that's what we are looking for the solution, and the search space x belonging to -10 to 10. So the solution lies within that closed interval. Okay. So A, if the initial solution, if the initial solution is x naught equals 3 and the temperature the temperature T naught is equal to 1.0, how would you generate a neighboring solution? How would you generate a neighboring solution? That's the A part. And B now, if f of x naught is equal to 12 and fx prime is equal to 10, okay, should should the should the neighbor solution be accepted? Should the neighbor solution x prime be accepted? I mean, that's the yes, right? Because the evaluation of that neighbor solution is 10 is less than 12. So, I mean, I've helped with that, right? So, and I've given you the reason. Should the neighbor solution x prime be accepted? And the question is why or why not? I've also given you that. So that goes. All right. So let me see your answer to this question in the comments, either on Facebook or on YouTube. Then, of course, you can copy the Python code from Facebook and try it out to see what you get. You just need to change the function and some other parameters here. Of course, here I did not give alpha, so you can use your own alpha. You can just tweak alpha and see how these things go, right? All right, so also let me know in the comment section how helpful these videos are. Let me know if there's a topic you'd like me to teach you, a problem you'd like me to solve. If you have subscribed, thank you. If you have not, please go ahead and subscribe. And everybody, don't forget to hit the notification bell so you can always get alerted each time a new video is released. And like and share also so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.